Speech recognition is a fascinating field where we can teach computers the ability to recognize spoken words. This is still a relatively novel way to interact with computers, but it has a variety of uses, from speech to text to being able to control your phone or smart speaker without the need to use your hands. In fact, powerful computers can use natural language processing to understand complete sentences and questions, but we're a lot more limited when it comes to microcontrollers. For the most part, microcontrollers are limited to being able to understand a few spoken words at a time. So in this episode, I'm going to show you how to train your Arduino to recognize a couple of custom keywords. We'll be using the Arduino Nano 33 BLE Sense as it has a beefy processor and a built-in microphone. We're going to use Edge Impulse to train our neural network. Note that Edge Impulse generates a library for us to include in our Arduino project. Right now, it only works with the Nano 33 BLE Sense, but I imagine with some effort it can be ported to other Arduino boards that have similar specs. I've put together a Python script to help us prepare our training data, which you can find in my EI keyword spotting repository. There is a notebook that you can run in Colab that will walk you through using the Python script, but I'd rather show you how to do it manually on your local machine. So let's download the repository and unzip it. Note that Windows will likely struggle with some of the path lengths, so I recommend using a program like 7-zip. We'll want to copy the dataset curation Python script and utils.py to someplace on our computer. Let's take a look at the code. Note that you'll need to have the NumPy, Librosa, Soundfile, and shutil packages installed to run the script, which I'll talk about later. I've included an example call so you can see what you'll need to run the script. Ideally, you'll want to start with the Google Speech Commands dataset and add your own custom keywords in another folder. The script will mix them together to create an output directory structure that looks like this. The noise category is just random snippets of background noise. Unknown consists of random other keywords that are not the target keywords. The target keywords will have their own directories inside the main output directory. The script takes care of augmenting the data by mixing random bits of background noise with each keyword to help make the model more robust. When the script starts, it will read the arguments and set up the output directory structure. It then goes through each clip of background noise and extracts some random segments of it to create a bunch of smaller noise clips. Next, it takes a random assortment of samples from one of the target keywords and mixes those samples with background noise. It repeats this process for all of the target keywords you tell it. Finally, it grabs the keyword samples that aren't targets and mixes them with background noise before saving them in the unknown category. In essence, what the script is doing is gathering samples from multiple input directories and curating a dataset that we will send to Edge Impulse. The target keywords we want it to listen for are in separate directories. A random selection of other words make up the unknown category, and random bits of background noise is the noise category. Additionally, the script is automatically adding in background noise to each sample to help make the model more robust against noise. Before we run the script, we need to collect some samples. I recommend starting with the Google Speech Commands dataset. Finding it can be a little tricky. If you search for it, you'll likely find a link to Pete Warden's blog post where you can download the first version of it. To get a more recent version, you'll need to click on the training link, which takes you to the TensorFlow repository. In that Speech Commands directory, click on the tutorial link in the README. That tutorial has a link to the more recent version of the dataset, so we'll download that one. When it's done downloading, extract the archive. Once again, if you're on Windows, I recommend 7-zip. Because this is a large dataset, it will take some time to unzip and unpack everything. I recommend unpacking the tar file into a Speech Commands dataset folder. When it's done, move the Speech Commands dataset folder to some location where you keep datasets like this. Go into that folder and move the background noise folder out, as the curation script needs to have background noise samples separate from keyword samples. You're welcome to pick some of the keywords available in the Speech Commands dataset, but I'm going to show you how you can make your own custom keyword because that's way more fun. Create another folder named Custom Keywords. To create a custom keyword, you first need to pick a short word or phrase and then record it a whole bunch of times. The best device to record it with is the device you plan to use for speech recognition because it's using the same microphone. In this case, that would be the Arduino, but I have found that a computer or a phone work just fine for this. I recommend getting about 50 samples to start with, but what you really want is to have a lot of different people with different voices, genders, inflections, and accents submit samples to this. That will help you train a more robust model that responds to something that's not just your voice. So for that, I recommend aiming for about 1,000 samples, but 50 is a good place to start. All right, what should I use as a keyword? I know. Digi-Key. Digi-Key? Digi-Key. 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 Once we've recorded a bunch of samples, we first want to create a new folder in our custom keywords directory with the name of our keyword. The name of this folder is important, and it's what our script will use to identify samples with a particular label. Next, we'll go into our recording device, which is my phone for me, and copy the audio file to somewhere else on the computer. Then, we need to use a program like Audacity to edit the file. Since our microcontroller only operates on 16 kHz audio, we should change the project to 16 kHz. This also matches the sample rate of the other Google Speech Commands samples. I recommend resampling the entire recording to match that sample rate. From there, we need to select 1 second of audio around each utterance and test playing it. Digi-Key. Make sure the sample sounds okay, and export just the selection as a WAV file. 32-bit float works as that matches the bit depth of the other samples. We repeat this process for every occurrence. Drop any samples that take longer than a second or do not contain the spoken keyword. Notice that I'm selecting exactly a second. This is not strictly necessary as the script will drop anything that's over 1 second or pad zeros onto any sample that's less than a second. However, you don't want to cut off any part of the spoken phrase. I'm also trying to vary when the utterance starts in each sample. The more variation in pitch, pronunciation, and location in the frame, the more robust model it will make. Finally, don't worry about the file name of each sample. The script will randomize the files and give them new names anyway. I've also found that phrases with more syllables perform better than short monosyllabic words. When you're done, you should have a nice collection of samples. I've got 68, which should work for this prototype. If you're on Windows, I definitely recommend using Anaconda as it makes managing some of the Python packages, like librosa, much easier. If you haven't done so already, use pip to install librosa, numpy, and soundfile. You shouldn't need to worry about shutil as that comes with Python. Note that I'm using Python 3.7 for this. When that's done, navigate into your speech recognition directory. Let's call the curation script with Python and feed it some arguments. First, we need to determine which keywords we want as our targets. We'll obviously go with our custom keyword, and let's pick something else from the Google Speech Commands dataset. I'll go with, well, go. You can have one or more keywords that are separated by commas here. Note that I don't have much luck with more than about 2 keywords, but you're welcome to try. You just might need to adjust the neural network we use later. Next, we give it the number of output samples per label we want the script to produce. I find around 1500 works pretty well. Then, we define the utterance volume, which I'll keep at 1, meaning there's no amplification. The G parameter is the background noise volume. I'll set this to 0.1 so that it reduces the mixed noise volume to 10% of the original. S is the sample time, which we want to keep at 1 second since that's how long all of the samples are. R is the sample rate, which we'll set to 16,000. Note that this script will resample any input audio files to this given R value, so your raw files do not need to be all the same sample rate. E is our bit depth, which we'll put at 16-bit PCM. That means our input files will lose some resolution from 32-bit float, but since our Arduino's microphone samples at 16 bits, we need the output training files to match that. Next, we define the location of the background noise samples, which we pulled out of the Google Speech Commands dataset earlier. O is our output directory, and then we list all of the input directories containing raw audio samples. There's no parameter label for input directories, so you can list more than one. The script will mix them all in. We'll then tell the script to run and go grab a snack. When it's done, feel free to check the results. You should see a set of folders named after the desired labels in the output directory. The unknown directory contains a random assortment of non-target keywords. Try opening one of the samples and playing it. You should be able to see how the background noise was mixed in with the original utterance. Digi-Key. Head to edgeimpulse.com. Make an account if you don't already have one. Log in and create a new project, which I'll call Speech Recognition. Go into that project and click on Data Acquisition. Click the Upload Existing Data button and click Choose Files in the new screen. We'll upload samples from one label at a time, so select all of the samples from the noise category and click Open. Let Edge Impulse automatically split between training and testing data, and let it determine the label from the file name, which is just the string before the first period. Click Begin Upload and let it run. Repeat the process for the unknown, DigiKey, and Go categories. This will take some time depending on the speed of your internet connection. When that's done, you should be able to go back into data acquisition to see all of the samples that you uploaded. I recommend verifying that about 20% of your files ended up in the test set and the rest in your training set. And you should also check that the labels were correctly read. Go into Impulse Design and click on the processing block icon. Edge Impulse recommends using the MEL frequency cepstral coefficients as features for spoken keyword spotting, so let's select that. Click on the flask icon to create a learning block. Once again, the default neural network that Edge Impulse recommends is the best for this application. Click Add and click Save Impulse. Go to the MFCC part of your design where you can see how each sample will be converted to its respective MFCC components. Feel free to play the sound samples and look at the output MFCC features from this block. Click on the Generate Features tab and then click Generate Features to let Edge Impulse calculate the MFCCs from all of our audio samples. When all of the features have been extracted, head to the NN classifier section. Here you can play with the neural network parameters if you'd like, but I find the defaults work pretty well. We're using a one-dimensional convolutional neural network with a few dropout layers to help reduce overfitting. Click Start Training to let the model begin training on our data. While that's going, note that you can construct your own neural network using their graphical tool. Or you can click on the pop-up menu to switch to expert mode if you know how to use Keras. Here, you can define the model manually in Python, but I'll leave it alone and let the model finish training. When training is complete, take a look at the console output. You definitely want the loss to be lower than on the first training step, and both accuracy measurements should ideally be above something like 80% for a task like this. Scroll down to find a confusion matrix checking the performance of our model. The rows are the actual labels, or ground truth labels, and the columns are the predicted labels. The numbers in the diagonal, where the predicted label is the same as the actual label, should be much higher than the other labels, which show false negatives and false positives. We also get a general score for accuracy, and 90% looks pretty good. The real test is trying the model on unseen data, which we can do in the Model Testing section. Select all the samples in the test set and click Classify Selected. Let that run for a minute. As you can see, the model performed much worse on unseen data. Because the model did better on training and validation data than it did on the test set, it likely means that the model overfit the training data. There are a few ways to combat this, but it involves playing with the model's hyperparameters, like the number of training steps, and trying out different neural network configurations with maybe more layers or changing the number of nodes in each layer. However, if we scroll through the test results, we see that Go performed very poorly, but Digi-Key did very well, once again confirming my observations that multisyllabic words and phrases perform better as keywords. I'm going to call this good enough for now and head to the deployment page. Edge Impulse gives us a few options to package up our model. The generic C++ library is great for general microcontroller usage. Cube AI works for STM32 parts, and WebAssembly is good for JavaScript environments. For our purposes, let's go with Arduino. We could have it build a ready-to-go sketch for the Nano 33 BLE Sense, but I'd rather show you how to use it as a generic Arduino library. Feel free to run the optimization analysis to get an idea of how much space and processing power the model and library will take up. You can see that it should take around 5 kilobytes of RAM and 36 kilobytes of flash for the neural network part. It should take about 4 milliseconds to run inference with the neural network on an 80 MHz microcontroller, but that does not take into account the time required to compute MFCCs, which is a lot longer. The confusion matrix shows us a summary of the test set results we looked at earlier. Click Build to generate and download the Arduino library. In a new Arduino sketch, go to Sketch, Include Library, Add .zip library, and select the .zip file you just downloaded from Edge Impulse. Go to File, Examples, and locate the library you just installed. Note that you might need to reload the Arduino IDE for this to appear. The name should match your Edge Impulse project name, so it's speech recognition for me. Open the microphone continuous example. Feel free to look through this example sketch to see how everything is set up and what functions are being called to make inference happen. Note that we define a slices per window number, which tells us how often inference is performed. Since the window is 1 second in this case, we run inference 3 times per second. In setup, you'll notice there are some EI_printf statements. This function is used to print strings to the console and is needed by some of the back-end library functions for debugging. If you dig into the implementation, you'll find that it uses the serial print functions on Arduino, so it's not much different than serial.print here. The sketch then calls the Edge Impulse init function, which sets up all of the necessary MFCC and neural network functions. In loop, the code first waits for the microphone buffer to fill up. It then calls this runClassifierContinuous function, which calculates the MFCCs from the captured audio and runs inference using the neural network we created. Once per window, or once per second in our case, the sketch prints out the results of the neural network inference. To figure out what our target classes are, we need to look at the index of this classification variable. To find it, you'll need to go into the Arduino libraries folder on your computer and go into the speech recognition library you just installed. Note that this library not only contains all of the necessary TensorFlow Lite functions to perform inference, but also the model that you created on Edge Impulse. That model is stored in the TF-Lite model directory as raw bytecode. However, what we're looking for is in model parameters, model metadata.h. This holds information about your model, including the list of labels in an array. The ordering is what's important here, so to identify the Digi-Key label, we need to use an index of 2. Back in our code, let's set up the Nano's onboard LED to blink whenever it hears Digi-Key. We'll start by making the LED pin an output. We want to compare the output value to a threshold every time inference is performed. We do this just before the section that prints out the results, which only does so after every 3 inferences. Remember that to access the Digi-Key label, we need to use 2 as our index. The output value is essentially a probability between 0 and 1, noting how likely the model thinks it heard the target keyword. 0.7 seems like a good place to start. If the value is higher than 0.7, we'll turn the LED on. Otherwise, we'll turn it off. Select the Arduino Nano 33BLE as your board, which should be in the NRF528X category, and select the serial port associated with the board. Click Upload and wait. If you're on Windows, you'll probably get an error telling you that some of the file name and extensions are too long. The Edge Impulse documentation mentions this in their Arduino section. The fix is to save the platform.local.txt file in the directory specified on that page, which is C, users, your username, appdata, local, Arduino 15, packages, Arduino hardware, embed 1.1.4. Feel free to take a look at what's in that text file. Go back to Arduino and try uploading again. Note that building takes quite a while as there's a lot in the library that we downloaded. When it's done, you can see that it uses around 230 kilobytes of flash and around 45 kilobytes of RAM for global variables. The Nano 33 BLE Sense likes to change serial ports during the upload process, so make sure you have the correct serial port selected. Open the serial terminal and watch the output. This should tell you that MFCC feature extraction takes about 261 milliseconds and neural network inference takes about 13 milliseconds. That means the processor is fully loaded, classifying audio slices for 274 milliseconds out of every 333 milliseconds, as this is running 3 times per second. That's about an 82% utilization, which means there's not much processing power left to run your code. You'll need to be careful about how you implement your code in this sketch, or you'll find that it will start missing audio samples. Alternatively, you could consider using the Nano as a coprocessor that just handles audio inference, and it sends notification via GPIO or other interface when it hears one of the target keywords. When I say go, you should see the probability of the go label go up, and when I say Digi-Key, you should see the probability of that label go up. I've found that for this board, you need to be close to the microphone. You could amplify the captured signal in code, but I'll leave that as an exercise for you to try out. As I mentioned, I need to be pretty close to the board for it to recognize the target keyword. So when I say Digi-Key, the yellow LED should light up. Digi-Key. I hope this video has helped you create your own custom keyword spotting and speech recognition device with an Arduino. Please subscribe if you want to see more videos like this one, and happy hacking!